So today's topic is what is a transistor and how to use it. So let us look at the definition of a transistor. The transistor is a 3-pin semiconductor device which is capable of amplification as well as rectification. Now let us look at the types of the transistor. The transistor can be broadly classified into two types: the BJT, that is the bipolar junction transistor, and the FETs, that is the field effect transistor. Again, the BJT can be classified into NPN and PNP. NPN means there are the two junctions, that is a NP junction and a PN junction, that is three layers total, NP and N, and the other type is the PNP, that is a N layer sandwiched between two P layers. Again, here the FETs can be classified in two types, that is the junction field effect transistor and the metal oxide semiconductor field effect transistor. Will come at the discussion of the FETs later in some later videos. Today I will discuss about the BJT, and in BJT I will discuss I will show the practical by using this NPN transistor. So okay, let's go to the theory. At first, let's take a look on how they looks actually. So this is a BJT, the bipolar junction transistor of NPN type, and they are the MOSFETs. You can see here the IRF 640N type MOSFET, that is a N-channel MOSFET. I will discuss about these MOSFETs in some later videos. Today our discussion will be centered between these NPN transistor. So let's start. At first, let's take a look at the pins of the transistor. As I had told already, the transistor is a 3-pin semiconductor device. It has 3 pins: the emitter pin, base pin and the collector pin, and all these pins are connected to the specific layers. If we consider a PNP transistor, then the emitter will be connected to P, the base will be connected to N, and the collector will be connected to C. And according to the connections of the transistor can be operated in 3 modes. They are the common emitter mode, the common base mode and the common collector mode. Let's take the example of a common base mode and using a PNP transistor. Now this may be considered as a structure of a transistor. You see this P layer, N layer and a P layer for a PNP transistor, and this is the emitter pin, this is the base pin and this is the collector pin. Now for normal operation, the emitter base junction is to be forward biased, that is this junction must be made forward biased, and the base collector junction, that is this junction, it must be made reverse biased. So in this case of PNP transistor, I have made forward biasing. How? I have attached the plus end of this battery or the source to the P and the negative end of this battery to the N side, so current is flowing in this direction, so it is forward biased. Again, here I have connected the negative end of the source to the P side and the positive end to the N side. You see, it's connected to the N side, so current is flowing from N to P, so it is reversed bias. So let's take a look in the current components which are flowing through the PNP. According to convention, we will consider all the currents are entering the transistor. So this is the direction of the emitter current, this is the base current and the collector current, but the sign in front of them will determine in which direction they are flowing, but conventionally we will consider that these are flowing inside, so we have considered positive here. Now let's check about the current components. The emitter current here is constituted of two types of carriers: the IEP, that is carried by the holes, that is flowing from P to N, and the IEN, that is carried by the electrons. So now since the concentration of electron here is greater than that of the P, the electron will flow in this direction, so the current will flow in this direction. But since the electron is emerging from N and going to P and not going to the P of this side, then this current will stop just in the base. So this is the end of this IEN, but IEP is not stopped in the end, since due to two reasons: the N layer is small, So all the holes are not recombined in the n layer with the electrons, so most of the holes just bypasses through this n layer and go to the p of the other side, and it is called IC1P. So it bypasses the base and goes to the p of the other side. But during this bypassing action, a little amount of current will be wasted here due to recombination in the n, since the current is flowing due to the holes, and the holes will be recombined here and the other part of the current will bypass in the collector. Again, in the collector, since the junction, the base collector junction is reverse bias, a reverse saturation current will flow from the collector to the base. This ICO is the reverse saturation current, which is constituted of these two components, the ICOP and the ICON. So overall, these are the current components flowing in the transistor. So taking some approximations and neglecting the currents which is constituted by the Ns, that is the electrons, we can say that the emitter current is constituted of the IEP, that is, it is almost equal to IEP. The base current is almost equal to IEP minus IC1P, that is this IEP minus IC1P, which will give this current component, and the IC is almost equal to IC1P, that is IC1P. Since I am considering only this IC1P because this IC1P is much greater than that of the reverse saturation current, that is the ICO. So that's all about the current components. Now let's take a look on the sign which we use to represent the transistor. This is a NPN transistor, the E, B and C terminals of this transistor, and this is a PNP transistor, the E, B, C are here. How can you remember the NPN transistor? That is, here the current is going out, we can say that it is nickel or N, and for PNP the current is entering, that is probesh, so PNP. So I have drawn two circuits in the common emitter mode. First case in using a NPN transistor, and in second case using a PNP transistor. So this B junction is forward bias, you see, NPN, so positive in P, and here the PNP, so negative in N. Now we will take the directions of the current which are entering this transistor to be positive, and the current which are going outside to be negative, and the voltages, suppose VBE. So the B and E are the subscripts. Now if the first subscript is greater than that of the second subscript, then the voltage will be taken as positive. For example, VBE, if the potential at VB is greater than that of the VE, then we will consider VE to be positive. So let's make a table here. In the first case, the PNPN transistor. So in NPN transistor, in this case the VCE. Now VCE means the potential between these things, these two. Now the plus is connected to C and minus is connected to E. So C is in greater potential than E, so VCE is positive. So we will write a plus here. In VCB, that is here, the source voltage is greater here than that of this. So the potential at C is greater than that of B. So it is also plus. Now VBE plus here and minus here. So it is also positive. Now for currents, IE emitter, it is existing from the E, so it is minus. Now B, current is entering through B, so IB is positive. Here the current is entering through C, so the current is positive. Okay, that is the table. Similarly, so in the same way for the PNP transistor, we will consider these signs. So you see there, it's totally opposite to that of the NPN. So that's all about the transistor, And now let's look at the output curves. So this is the circuit configuration in which we will determine the different characteristics curve, the input, that is the transfer characteristics, and the output, that is the drain characteristics. By input characteristics we mean the curve which is created by varying the VBE and noting the different currents for it, that is the IB, that is VBE versus IB, taking VCE is constant. This is VCE, that is the voltage between the C and the emitter terminal. And by output characteristics, that is the drain characteristics, we mean the change of IC with respect to the change of the VCE, keeping IB as constant. This is VCE, so we will change this VCE and note this IC, and we will keep this IB as constant. So by this, now the input, that is the transfer characteristic curve, looks like this. The x-axis is taken as the VBE and the y-axis is taken as the IB, which is scaled in microampere, and in the x-axis it is scaled in volt. So by increasing the voltage, the current will drastically increase, keeping VCE constant. So this is the input characteristics of the curve. Now if we increase VCE with the increase of VBE, or if we take this at constant VBE, then for a higher value of VCE, the value of IB for the same VBE will be lower. Now this is our output characteristics, that is the drain characteristics of the transistor, where the x-axis represents the VCE, that is the voltage between the collector and the emitter terminal, and IC, that is the collector current, which is scaled in milliampere. The first one is in microampere and this is milliampere. So at IB 0 microampere, this is the characteristic curve, and with the increase of the base current, that is IB, the value of the collector current will also increase, but beyond IB equal to 0 there will be no collector current, so the transistor will become off. So we can say that for a constant VCE, that is this, if we cut a line parallel to the y-axis, we can say that for a constant VCE, the IC increases with the increase in IB. So since IC is the most important parameter for a transistor, and IB controls this IC, so the transistor may also be called as the current control device. And before going to end this topic, let's get accustomed with the different regions of the output curve. At first, when the current is increasing exponentially, that is the collector current is increasing exponentially with the small increase in the VCE, this region is called as the saturation region. From this region to this part is called as the saturation region, and that is the on state of the transistor. And when IB and below IB equal to 0, when there will be no current, that is IB is negative, the transistor will be remain off, that is the cutoff region, this part. And between the saturation and the cutoff region, this is the active region. Here the transistor will act as a amplifier. So here the off state of the transistor, here the amplification purpose, and this is the on state of the transistor. So that's all about the output characteristics curve. And at last, why transistor is called as transistor, that is the why it's named so. You see, the current is transferred from the emitter base junction to that of the collector base junction, that is here. The current is transferred from emitter to collector through base. But you see, this is the current in the input circuit, and it's transferred to the output circuit. But in the input circuit, the junction is forward biased and the resistance is low, but in the output circuit the junction is reverse biased, that is the CB junction is reversed biased and the resistance is higher. So current is transferred from the circuit of lower resistance to the circuit of the higher resistance. So this is called as the transfer resistor or transistor.